2 of our Eastman Chemical Company Science Seminar. Today we have with us our friend, a chemical engineer. He'll introduce himself. He's a graduate of Texas A&M, I believe.
Yes.
And he's been here for a long time at Eastman, haven't you? How long have you been?
34 years.
34 years,
yeah,
so yeah.
Not that long for some of us.
So, last week we talked about some of the chemistry that went on. Now you're going to hear how the chemical engineers scale up that chemistry so they can make hundreds and hundreds of thousands maybe of kilograms of this stuff over some time periods and dump it into big rail cars and ship it all out to all kinds of different places. So let's give a warm welcome.
So Gary mentioned that a little bit about as far as the applicability, but I guess I wanted to touch a little bit about the company and what we do. And when you think about it, what we do and the products we make are directly related to not just chemical engineers, but chemists, mechanical engineers, civil engineers, all the technical folks that work in that type of arena. Just to kind of start off with a little bit, Gary kind of stole my second slide here, but graduated Texas A&M in 1982, been with Eastman for my entire career, which is kind of a different paradigm now. Most people come out and say, well, I'm going to work for 4 or 5 years and move to another company, but back then it was pretty typical that you came and stayed at the same company for your entire career. I'm married. My wife's Joan. We've got 4 kids. The first 2 daughters are married with cumulative 6 grandkids. Tim just graduated from Texas, the University of Texas, the other Texas, and he's actually over in Israel right now for a year mission assignment. And Emma's just starting college at Abilene Christian, so at least we've got empty nesters now. Everybody's out of the house, and the grandkids can come and visit. So I like bicycle riding. Joan and I actually met each other 25 years ago riding bicycles together. I like hunting, fishing, hiking, anything outdoors. So when you think about what Eastman is, and we kind of talk about it from that perspective, a specialty chemical company. I mean, I think that's one of the things. So what that means is we really like to sell products that are high value and directly to the applications, as opposed to commodity chemicals where you don't make a whole lot of money on them and you really struggle to find your place in the market. We've got about 15,000 employees, 50 different manufacturing sites across the company, and then really dedicated to environmental stewardship, social responsibility, economic growth. So in other words, I think if you interact with anybody from Eastman, you'll see those themes and inner guiding principles, that we really do care about the people, care about the environment, care about where the company is going. And we get a bunch of different awards and things like that. Wrong mouse. So just looking a little bit about where we're located, the dots are all the different manufacturing organizations that Eastman has. A lot's in the North America, but there's a lot of facilities in the Asia Pacific area and then in Europe also. So a lot of our people that come to work sometimes in Longview, I said, we typically, the current generations are moving around. Well, you actually can move around within Eastman and move to other locations potentially like that to support the overall corporation. Just a little bit about where do we sell? Where do we make our money? I guess when you're in business, that's what it comes down to is, but 45% of Eastman's revenue comes from the North America region, which is kind of interesting. If you go back maybe 20 years ago or so, it probably would have been closer to 80 or 90% in the United States. But really, it's a global company and global sales. The segments. The other thing is that we're not one segment. In other words, one business that we sell into a lot of businesses. The big ones being transportation and building construction. So you think about anything, how many cars and trucks are out there? There's a lot of them. It's a good place to make a lot of money, and a good place to have good products and things to sell into. So I want to just touch a little bit about, when you look at a car or a truck, what are those Eastman products that are in there? And then specifically, I was going to try to call out some of the ones that are Longview specific, that we make in Longview, that ultimately go into the manufacture of cars and like that. The windshields is one I was going to call out. When you look at a windshield, I don't know if you know, it's not just a piece of glass. If you've ever broken your windshield, it doesn't just fall apart. There's a layer of glass, there's a layer of polymer that's in there called polyvinyl butyrol, and then another layer of glass. And what that polymer does is not only from a safety standpoint, keeps it from coming apart, but it also allows you to do noise dampening. Some of the newer cars, how quiet they are when you get in. Well, it's because they're dampening noise with that polyvinyl butyrol. Well, in Longview, we make the normal butyraldehyde, which ultimately goes to another Eastman site to make the polyvinyl butyrol. So how you customize those polymers and how you make those polymers so they're optically clear, and then they're also introduce the acoustic characteristics that you want to have, and the weight characteristics, so you have energy efficiency and all of that. So windshields, Eastman's big into the inner layers. Eastman plasticizers down on the bottom. Plasticizers, does everybody know what a plasticizer is? Maybe not. If you look at polyvinyl chloride PVC pipe, the white pipe is rigid like that. Well, if you take an organic plasticizer and mix it with the polyvinyl chloride, it becomes flexible. It becomes flexible like wire coating. When you take the insulation on wire, it's nice and flexible. Well, it's because you've taken that rigid PVC and plasticized it. Eastman makes the plasticizer. So in Longview, we're making a Texanol isobutyrate plasticizer and a 2EH-based, 2-hexanol-based plasticizer. So we're making lots of, quantities of these plasticizers, then ultimately go get processed and make their way into the cars. There's a number of other ones. I'm going to move to the next one. When you think about building and construction, a lot of stuff is in building and construction. So when you think about, if you want to focus a career on things, you see things like up here in the Texanol. I don't know if you can see that under the Gila. Texanol is a Eastman-developed molecule that we make here in Longview that really makes latex paint what latex paint is. It's a coalescing aid that coalesces the pigments and basically makes the paint dry in the way it does. But anything latex is related to that Texanol. So that's one of the products we make. Eastaflex is kind of an interesting product. It's actually a tackifying resin. So it actually, you can use it in roofing, you can use it in sealants, like window sealants. They also call out the Saflex residential or architectural glass, very similar to the glass on windshields. They're putting that now in buildings, in houses. You can think about, if you're in hurricane-prone area, wouldn't you like to have a window that when the wind blows it doesn't break, or something hits it, it stays intact, and also gives you acoustic characteristics and insulation characteristics. So again, Eastman's finding itself in a lot of different places. And when you think about careers, you might be a polymer scientist, or you might be a basic organic chemist, in the more of the small molecules. But there's lots of places to play in and lots of specialties that you could have. So kind of, that's the company. There's lots of things in Longview. So I wanted to spend a little bit of time talking about what Longview, Texas operations are. That's what we call ourselves. And I stand behind y'all. I'm trying to step back. Can y'all? You're good. Okay. But we make a whole family of chemicals, things called olefins. So we'll talk a little bit about more of those. But olefins being an unsaturated you can think about a paraffin like ethane, and you unsaturated it to ethylene. That's what we call olefins. Alcohols, it has an alcohol group in it, like methanol, ethanol, propanol, butanol, basically. From that, aldehydes are basically the unsaturated alcohols. In solvents, resins, in all, there's about 35 or so chemicals that we make that are specific chemical elements, you could say it that way, at the Longview site. We sell those into a bunch of different markets and trade names, so there's multiple commercializations of products, but really when you look at the molecules we make, there's about 35. We got mentioned the corporation has 15,000 employees, we've got 1,500 employees, and that's basically, there's two big sites, the Kingsport site, the home office with about 10,000 employees. We're the second largest at 1,500, and then the rest of the plants are small, maybe 100 employees, 80 employees, 150 employees. But we do sell, or what leaves the plant, about 4 billion pounds a year. So you mentioned about kgs, that's like, convert 4 billion into kgs real quick. I'm not sure I can do that in my head, but it's about 2 billion, or 2 million met tons of material a year, so somewhere in that kind of range. So you think about, I don't know if you've done any fluid flow type calculations, you may be you're talking like 1,000 gallons a minute of product leaving the plant day in and day out. It's those kinds of volumes that you're talking about. So logistics of how do you handle that amount of material all the time, every time, bringing in the feedstocks and getting the products out. So one of the main things that we start off with, and I mentioned about olefins, is our hydrocarbon cracking process. So hydrocarbon cracking, essentially what we do is we take the oil field, the gas, the ethane and the propane, which is the light part of the natural gas. Natural gas is mostly methane, but it has these ethane and propane in it. We take those and actually go through what's called a hydrocarbon cracking, because we are thermally rearranging the product and cracking off some hydrogen to make a mix of everything from hydrogen down to what we call pitar. Pitar being like heavies, pi gas, maybe C5s, at the C7s type range. But really we try to control that distribution in that process to preferentially make ethylene and propylene, which are feedstocks. So what a cracking plant is you start off, we talk about thermal cracking. So it's basically big furnaces with tubes that run through them, and you run the ethane and propane and run them up to maybe 1,400 degrees Fahrenheit. I could convert to degrees C. We deal in the SI system versus the metric system. So one of these days we'll switch over, but it's pretty hot. And then we run it through at less than a half a second of residence time, and you quench it quickly. So what you're doing is you're kicking off these hydrogen and making the heavies, but you go from those furnaces to a heat recovery, heat generation. You're extracting the heat out and cooling it down quickly. You think about from a mechanical standpoint, a lot of I assume there's mechanical engineers in here, mechanical intensive type process because of the thermal stresses and the things that you see in a furnace, and then trying to cool it down real quick. From there it goes into a compression and chill down, so we start compressing the material up in a 5-stage compressor and knocking out liquids as we go. So we knock out the heavies, and ultimately what we're trying to do is chill this down to the point where we can liquefy methane. So liquid methane is pretty low temperature, cryogenics. So you go all the way from a furnace to cryogenics in this plant, and because ultimately you want to refine and separate the hydrogen from the methane, and then the methane from the ethane, and the ethane from the ethylene, and continue down. So you have all that type of separations occurring in a distillation process or fractionation process, just like you'd see in the chemistry labs, in your distillation operations. These are just done on much larger scale. You know, the columns might be 200, 250 feet tall. You know, huge columns processing not only in the cryogenic mode, but in more ambient type temperatures. So we run our cracking plants. I'm going to go back to this kind of overall process flow diagram, just to kind of come back to it. But you see at the beginning, I kind of have put the hydrocarbon cracking as kind of our starting point, where we make the ethylene, we make the propylene, we also make the pi gas we use in the hydrogen. You know, when you look at the drawings, they're, in addition to the cracking plant being like a big synergy point where there's a lot of different streams coming out of it, OXO is another area that is a lot of synergies. So I'm going to talk a little bit about it. So what you do in OXO, and I guess Damon did. How many were in Damon's presentation last week? So he was talking about the chemistries, hydroformylation going on in OXO. And so what we do in there is we take an olefin, either ethylene or propylene, and syngas. Syngas means synthesis gas, where you have a 50-50 mixture of hydrogen and carbon monoxide. And you react those to these aldehydes. So an ethylene with syngas goes to propionaldehyde. A propylene with syngas goes to a mixture of two isomers of C4 aldehydes, the iso characteristic or the normal. Normal meaning a straight chain, iso meaning a branch chain. So I wanted to touch a little bit on syngas. You know, syngas operation is kind of unique. Not a whole lot of companies practice it. What we're doing is, you know, we're practicing a process called partial oxidation. So again, if you're a mechanical engineer, this might resonate with you. But you run, you have a reactor that's running at about 2,500 degrees Fahrenheit and about 600 pounds of pressure, and you're feeding natural gas and pure oxygen into it. And starving it for oxygen so that it doesn't burn all the way to water and CO2. So you're stopping it there. Now you got this gas at 2,500 degrees, and then you got to transition it down to ambient conditions. Well, you're going from refractory to hot surface hot surface heat exchangers, and metallurgy-wise, it actually burns back the metal if you don't design it right. So there's the metallurgy and the mechanics of how you do that transition of those high temperatures to lower temperatures is pretty intricate. You know, obviously when you're hot, you want to recover all the energy you can, so we have steam generation, heat recovery type operations, so from that optimization. The other thing we do is then we have to remove the carbon dioxide, and most companies vent the excess, the unreacted carbon dioxide. But what we're doing is, you know, absorbing it, recovering it, compressing it, putting that CO2 back into the feedstock. So when you look at a carbon footprint, and I don't know if you've heard that terminology, you can look at a process of, you know, what's the true carbon footprint. We actually have a negative carbon footprint. We use all of this, we recycle the CO2 to completion, and we actually have streams from within the plant, other streams that are producing carbon dioxide. We're capturing that and putting it back in here, making syngas out of it. So it's kind of a unique, I think we're the only company that actually does full CO2 capture, control, and recycle to completion. So, you know, kind of a unique thing there when you calculate those CO2 footprint type calculations. OXO is another one, and I'm not going to touch on this too deeply, but basically, Eastman developed this technology that we're doing back. I guess we've actually put it into commercial operation in 1988. Had another generation of catalysts go in that we've upped the catalyst. But so again, our research and development labs in Longview developed that process. We call it a low pressure process because it runs at about 300 psig. The old process was a high pressure 2500 psig. So you can imagine the energy efficiency of not having to compress everything up and run at those kinds of high pressures, and then have to deal with the reliability of the mechanical equipment at that kind of pressure. Just a couple other things. It's the world's largest oxoaldehyde facility. So we're pushing through there, approaching 2 billion pounds a year of product. So I mean, it's pretty amazing that you get to work on a world-class, world-scale facility. So kind of back to here. And what I wanted to do is, for a couple of the other areas, talk a little bit about, what are the products that come out of these plants, and maybe a little bit about the chemistry. But aldehyde reduction is the department that we call, and what when we say aldehyde reduction, what that means is we take an aldehyde, hydrogenate it to its reduced form. It's to the alcohol, essentially. So it's the reduction of the aldehyde to an alcohol with hydrogenation, essentially, is what that terminology is. So when you look at like normal butanol, you take normal butyraldehyde that you produced in oxo, you hydrogenate it to normal butanol. Sounds pretty simple. The process is not as intensive as the oxo or the cracking plants, but again, it's a reaction and how you control byproducts and co-products that go on in that hydrogenation at the same time. But it goes into, it's a solvent. Ultimately, a lot of it goes to our Kingsport, Tennessee location, where they convert it to a normal butyl acetate, and that normal butyl acetate then goes into automotive paints as a solvent. So it's, it finds its way, we're industrial chemicals, add on one more industrial chemical and move it on into an end-use application. 2-ethylhexanol is kind of another kind of interesting material. We take two normal butyraldehydes and do an aldol condensation. So you combine the two together into an aldol condensation, means basically condensing and putting them together and kicking off of water. So now we have that. We hydrogenate it to the C8 alcohol and have 2-ethylhexanol. The kind of interesting applications is that 2-ethylhexanol is part of what goes into a plasticizer. And I mentioned plasticizers earlier. Well, that plasticizer is one that's qualified for the medical applications like IV bags and IV tubing, things of that sort. We also use, there's a lot of movement right now about the plasticizer dioctyl phthalate. I don't know if you've heard anything about that, but there's concerns about that material could leach out in toys for kids and then have some neurological issues. So the conversion is away from that orthophthalate, that octylphthalate plasticizer. These non-orthophthalate plasticizers, which 2EH goes into, is what the movement in the industry is for baby toys. So if you see the rubber ducks or anything of that sort, those non-orthophthalate plasticizers are what is making them safer than the ones that have been used for 40 or 50 years. Wire insulations, a PZ. Neopenyl glycol is another kind of an aldol condensation. You take an isobutyraldehyde and formaldehyde, and you put them together, and now you have a glycol. It has two alcohol functionalities, so it's a good polymerizing agent. So fiberglass boats, you polymerize NPG into making the clear coat on fiberglass boats, so those sorts of things. So a lot of different products come out of aldehyde reduction, but the core chemistries are that aldol condensation reaction and then hydrogenation. If you look at the theme for those entire set of products. Texanol is a material that was developed, I guess, back in the 1960s or so. It's an isobutyraldehyde material. I mentioned about it being latex paints, but basically it's 3 isobutyraldehydes, and we go through. It's called a Terschenko reaction, where they go together, form a trimer, and then break out into it's an ester alcohol. So it has ester functionality and an alcohol functionality. And works great for paint. I think we have 75% of the global market on latex paint, the Texanol that goes into that. You also can take that Texanol and esterify it further from a ester alcohol to a diester. And so that becomes a C16 plasticizer. We call it Texanol isobutyrate, or TXIB. So if people are allergic to latex, like latex gloves or those sorts of things, you esterify it, and then you can that becomes the plasticizer in vinyl gloves or vinyl flooring or vinyl water hoses. And people are not typically allergic to that, which is kind of unusual, how a small change add on a functionality and it changes how people are allergic to things. So a lot of the medical industry, if you're a nurse and you are allergic to the latex gloves, you switch over to vinyl gloves and everything's good. But Eastman has a part in that also. We actually oxidize with air some of the aldehydes. Just kind of interesting one. The propionic acid is goes into food preservatives like tortillas, animal nutrition preservatives, crop preservatives. They'll typically spray those on there from a preservation standpoint. So propionic acid is one that is near food contact. It's actually kosher. It's, in other words, it's basically you have to have those sorts of regulations and those sorts of quality control to be able to sell it into a product that actually is going to go for human consumption. And then we've got a bunch of other stuff too, so I'm going to skip on. Yeast attack. So if you're into the polymerization sort of chemistries, where yeast attack came from was we had this gas, which was roughly a C5. So you think about cyclopentadiene or dicyclopentadiene. What do you do with that to get rid of it? So they started looking at you could actually use it's a Ziegler-Natta catalyst chain propagation. So you actually chain it together with the catalysis, and then you chop it off and hydrogenate it at the end. Well, that becomes a tackifying resin. You can think about cereal boxes. That little strip of hot melt spray that's on that closes the top of the cereal box, that's yeast attack. The layers between how you put a diaper together, that you want them to stick together, and how those different layers stick together, that's yeast attack. So you can envision you want something that came out of as a kind of a crude material, but it has to be water white. You don't want a brown glue on your baby diapers, because it's that sort of thing. So there's a lot of chemistry. Yeah, or maybe you do. Maybe it gives you an indication that it's time to change. But anyway, things like that. That's what our chemists are working on. Is how do you make something that you can take these basically waste stream, that gas, turn it into something that is water white and near food contact, that you can spray on cereal boxes and not have a concern. So there's a lot of if you're a polymer chemist, a lot of those sorts of things going on. Ethylene oxide is a unique chemical. If you're a chemist, it probably would intrigue you that you can take ethylene and pure oxygen and turn it into this ethylene oxide. Very reactive, very hazardous material, those sorts of things, but it can quickly react. We don't keep an inventory of ethylene oxide. We react it into things like ethylene glycol. That's antifreeze, essentially, the old-style antifreeze. It goes into the polyethylene terephthalate water or drink bottles, like Coke bottles, things of that sort. But we also make there, you can react it to make EO solvents and glycol ethers and different molecules that we make at the site and react them. They go into basically industrial chemicals. Things like brake fluids, anti-icing for aircraft. You envision us selling out rail cars of this material, and some other company comes in and takes it and converts it into the brake fluids. And I think kind of the last area of this right here is related to acetaldehyde. So kind of another unique thing. We take ethylene and air and actually turn it into the C2 aldehyde, the acetaldehyde. We're the only producer of acetaldehyde in North America. And so kind of, it's a unique position to have that kind of a, time to take medicine, right? But acetaldehyde is kind of a unique. What it's used is in the pharmaceutical areas. So anytime if you look at your medicine bottle or your aspirin and you look on there and it says kind of an aceto group, it's coming from acetaldehyde. So it's in the pharmaceutical industry. That's what we sell a lot into. You can see some of the things there that it goes into. But again, again, look at those aceto groups, and that's an acetaldehyde. And I guess from the standpoint, at least from my perspective, I would sure rather have acetaldehyde coming from a U.S. producer than with a questionable quality from, say, South America or Asian or whatever like that. They're getting a lot better, but still, the quality control, and if you're using it in a pharmaceutical applications, there's some value at least having very, very tight control over those products. So anyway, some pictures, around the site, but in general, all of our material goes out of the plant site, mostly in rail cars, and the ones in the center there, and some out in trucks, tank trucks. Most of our material is liquid, in the liquid form. We do have some solids, that's bagged and taken out that way, but the majority of what Eastman makes is going to be in a liquid form. So changing directions here a little bit. What does a chemical engineer do? And the reason I wanted to talk about this a little bit is I know y'all are, or at least Laterno's moving towards having a chemical engineering curricula set up in the not too distant future, or maybe this coming semester. I don't know if that's where you are, but one of the things a chemical engineer does is looks at what we call unit operations, or what I guess another way of looking at that is building blocks. In other words, so you could become an expert in a furnace, or you could become experts in a reactor. When you put a plant together, you might need a furnace on, like the cracking plants, you might need a furnace on the front end, you need a compressor, you need some refrigeration, you need a distillation, you need heat exchange. You could put those blocks together so that when you're studying in college and then at work itself, people learn by those unit operations. And so you kind of you have experts that might have the expertise in distillation or in reaction or in furnaces, but you think about the whole process is a series of blocks that fit together. Within Eastman Chemical, at least in Longview, all of our chemical engineers come into our research and development organization. We actually call ourselves now Texas Technology, but it's research and development. But we also have roles in our engineering and construction. Typically, in engineering and construction, or you think about would be mechanical engineers, civil engineers, electrical engineers, but chemical engineers play in that world too, as far as the developing the processes, putting those blocks together, and then assisting with executing the projects. They can be in operations management, actually running the plants. There's a whole environmental engineering group. If that's, some people have a passion from an environmental standpoint, there's a place for chemical engineers there, all the way to business management. A lot of our managers that are in the business organizations had their start as chemical engineers. So kind of you think about roles of what a chemical engineer might do. One area we talk about is process optimization or process improvement. So you could envision, I've got some fired furnaces, like at the cracking plant. So I'd like to increase the efficiency of the firing rate versus what I need to get into the process. So you would potentially go in there and do some things like optimizing either the fuel to process ratio or the percent excess air, those fundamental calculations that you have for a furnace operation. You want to burn with as little extra air that you have, so you don't waste any energy. And you want to have 100% combustion of your materials so you don't exhaust combustibles like carbon monoxide out your stack. So you have optimization parameters. But that's the type of process optimization people do. We do a lot of designed experiments where you do like a matrix box of experiments and you hit each corner to try to develop multiple layers of trends and connections that way. We use a lot of Six Sigma, which is the applied statistics and things of that sort, and the tools, the project management tools in the Six Sigma arena. You know, some of our engineers are working in advanced controls. Kind of the terminology is model predictive control and engineered process control. So if people have a really desire to, be, and these are chemical engineers, electrical engineers, and also tend to play in the advanced controls area. But you start thinking about where you have a computer model, an engineered model that says, here's how it should run, here's how the process is running, and I'm going to move the process to match the model. Those are the types of things that go on. So we've gone beyond just a single loop PID type control logic to these advanced controls that are operating to move the plant in a more efficient fashion. Another thing that our engineers do is process development. You could envision, this continual journey to try to reduce cost, reduce energy consumption, be more efficient. And so if you look at your plant and it has 10 distillation columns to separate the products out, you got to ask the question, well, can I do it with 9 or 8 or 7 or 6? So redesigning the plant to the next generation of efficiency. All the way to developing new materials, new products, like this with the Triton polymer. We actually have one of the feedstocks started here in Longview, and the polymerization manufacturers up in Kingsport. But if you ever see those plastic BPA water bottles, BPA-free water bottles, that say Triton on them, well, that's Eastman Triton material. It's, I guess Camelback sells them, and those kinds of distributors. Also, they do a lot of environmental design. You envision we're on a journey to cut our energy intensity by 25% across the corporation over about an 8-year period. In other words, so cut a fourth of the energy use with the production you're making in 10 years. I mean, pretty challenging, because we're not just throwing energy away. It's continue to grow and continue to drive energy efficiency. So that is a focus for us. Reliability is an area that you might not think about, but our plants run 98% of the time, 24/7. Every minute it's down, it's not making money and not making pounds. So anything you can do to connect the operator that's running it to the distributed control computer that is actually making the changes in the plant, that's the human-machine interface. And how you build that so that it reliably functions and you don't have a person operator making an incorrect adjustment that's not going to be the best thing for the plant. So that we call that human-machine interface. Safety is another area. We want the plants to run safely. We want the people to be safe. We want everybody. I want to go home safe every day. I want to go home safe my entire career. I don't want to have an injury, and that's a belief. And fundamentally, you have to play in the process hazard analysis and management of change. So you do everything right, and you address any safety issues even before you venture off into changing something. Anyway, so it's think about it's the people. What excites me about coming to work every day, I get to be interacting with the people. And I think, some companies are only in it for the dollar at the end of the day, and that's not a motivating factor in the long term. But knowing the people and connecting, that's really. And I think if you ask almost any Eastman employee, that's probably what they're going to go back to is, why did you come to Eastman? Well, it was the people. going to touch on safety just a little bit, but really we truly believe that we can work in an injury-free workplace, and everybody should go home safely at the end of the day. Kind of our thing that we're, vision down in the last bullet there, because we care, we choose to act so everyone is safe. And what that means is if I see someone doing something that's going to get themselves hurt, I'm obligated to talk to them about it and stop it. I don't want to just walk off and say, well, I don't know who that is. It won't hurt them too bad. That's the wrong culture you want. You want people willing to step out there and actually act on those situations. So, you think about somebody walking down the hallway with their cell phone out reading it. Well, stop them and say, you're going to potentially, you can run into somebody, you can trip, you've lost your focus. I don't want you to fall down. I don't want you to bump into somebody, even to that level. So that's what the culture is that we have. Kind of the last slide I got here, so we do have some time, is, I mentioned at the beginning that we do have a number of awards that we've had over the years. I guess the ones that just jump out at me is up in the Partner of the Year on the Energy Star. So for the last 5 years, we've been at the highest level from an energy management recognition and continued reduction in energy, so energy efficiency. World's most ethical companies. How do you, that's something to be proud of. And then, best workplaces to work in the center there. That Glassdoor is continues to highlight Eastman as one of the best places to work. So, we're up there with the Googles and with the, that tier of companies as far as from a work environment that we have. So with that, I'm going to stop, I guess. You mentioned time for questions, so I tried to get...
Not the time for questions.
Yeah.
Good. I have questions for Mr. Slivensky today.
Yes.
Where's I saw there was a plant on the West Coast. Where is that exactly?
On the West Coast, it's actually it's in the Los Angeles area. It's a small polymer plant, I believe is what it is. So, I think it's very small, like less than 50 people.
Yeah, I think it was near where I used to live.
Okay.
That's why I asked.
Yeah.
It
Where
was
were
up
you at? Where were you living?
Ventura County.
Ventura County.
I've seen it too.
We actually, Eastman actually in the last 3 years has made some significant acquisitions. We've spent like $3 billion buying solutions. I believe it was a solution plant to go back 3 or 4 or 5 years ago. And I think that's what it is. Those kinds of things, when you think about a $3 billion acquisition to buy a bunch of plants, that's pretty significant. So,
Other questions?
What is something that you wish you would have done like in college to better prepare you to get into this? Is there like a class you should do more chemistry or anything like that?
Yeah, more chemistry.
Yeah. Actually, down at A&M, we actually took enough chemistry the same amount of chemistry that the BS level did to get the chemical engineer. So we had pretty, all the way through a couple of years of quantum mechanics and at that level. I think when I got out, we actually assembled a group and we started doing graduate chemical engineering with Louisiana Tech and worked on that. Because we were thinking, well, we missed something or we were behind. But where I think would be beneficial is an MBA to marry the chemistry, the technical side with the business side. And if you say one thing I would have liked to have had, and I guess I still can't go get it, but an MBA to marry and bring a business perspective along with that.
If somebody was to do like chemical engineering through Latrano, would you suggest doing both a major in chemistry and chemical engineering? So you just have that ability to go wherever with.
I don't, the paradigm I have is I'm seeing what Eastman does as jobs. And a chemical engineering job is completely different than a chemist's job. In reality, most chemists at Eastman, you gotta have a PhD. And if you want to be a full chemist, it's a PhD. So having a bachelor's in chemistry or a minor in chemistry, don't know if it gets you there. It can't hurt, but if you, again, I think you would say, I'm a chemical engineer, you will have a much better career path than a bachelor chemist, I think. Just my opinion. Within Eastman. Now, so other companies may think differently.
Other questions? If you're interested in the chemical engineering program at Paterno, it is in the catalog, I've been told, so check it out. It's found in the chemistry department, relationship with Iowa State University. So check that out. If you have more questions on that, you can come and see me at some other time. Let's thank our speaker.